All right, so this is example 4-1 in your book, and we're told that we have a biaxial stress element here. It has sigma x. It's positive, so we know that it's in tension. It's 40,000 psi, and we're told that we have sigma y, which is negative, and it is 20,000 psi. So this might be something that you get from your analysis. And then we're told that we have tau xy, that's positive, so we're going to draw it in the positive direction. Of course, they have to be equal and opposite to balance. And then we have tau xy, which is equal to tau yx, and it is equal to 30,000 psi. And in the book, they put this CCW for counterclockwise, and it's a little bit different notation than maybe what you're used to, but that means that would cause counterclockwise rotation. And when we plot the stress, we actually plot it with positive clockwise rotation. So so what we do is, the question is, well, how do we get this into Mohr circle? Well, if we're going to draw Mohr circle, we'll draw our axes. Okay, we'll draw our shear axis and our normal axis, and we'll start off with our points. So we're told that sigma x is 40,000 and sigma y is minus 20,000, so it's going to give us points on each side of the circle. So we'll have a point that is down here. Okay, we're going to have sigma x. Okay, so sigma x is going to be, oops, excuse me. Sigma x is going to be, I hit the wrong button here, sorry. Let me try that again. So we have our sigma x value, which is going to be 40,000, and then we have our tau x y value, which is 30,000, so maybe make that a little bit longer, and that gives us 1 point. And then we have the sigma y. Sigma y is 20,000, so it's going to be about half that guy, and then we use the same shear value here, and that gives us our point B. Okay, so this is point B, this is point A, and then this is our circle. We try to draw a circle here, so then we can find our average stress is going to be the middle. So the center is sigma x plus sigma y over 2. That gives us the point in the middle. We can note here that we actually know where our principal stresses are, okay, already, because we know that they're at the max. So we have this point here, okay, that will be sigma 1 because it's the max. We'll have sigma 2 is actually going to be here at 0 because we have plane stress, and we have sigma 3 here because that's our least value of principal stress. And then once we calculate our radius, this will be our max shear stress here. All right, but we actually have, in this case, we actually have 2 circles, right? So we have a circle here, and we have another circle here, and we have this third circle that goes around them. So our max end plane shear is actually this radius. It's just the max. A mistake that some people make is they'll take this radius as the max shear, and you can't do that. So we can find the center of our circle. If we want to find sigma 1, it's the center of the circle plus the radius. Sigma 2 is the center of the circle minus the radius, and then tau max is equal to the radius. Okay, so the radius from our equations is the square root of sigma x minus sigma y over 2 quantity squared plus tau xy squared. So if we solve for that, then we get that it is about 42,426 psi, and that is equal to the max in plane shear for that circle. Okay, it's also equal to tau 13, which is equal to the value, the absolute value between sigma 1 minus sigma 3 over 2. Okay, so that's this distance here, which is the overall circle, over 2 gives us our radius on each section. We also have the other principal shears, but we don't care about them because they're smaller. Okay, so we have the tau 13, we have tau 21, and that would be the stress from sigma 2, which is 0, minus sigma 1 over 2. Okay, and that would be this radius here. Okay, that would be the radius of this smaller circle. And then we have tau 31, which would be sigma 3, sigma 32, which would be sigma 3 minus sigma 2 over 2, and that would be this radius here. So that's the relationship between those equations that we showed. But what we care about is the max end plane shear, which goes for this overall, for the largest circle. And then if we do that and we calculate that, we find that the max end plane shear stress is this value here, which is that radius, and then we can find our principal stresses, and our principal stress is just equal to the center sigma c, this equation up here, plus the radius. And if we work that out, we find that the principal stress for sigma 1 is 52,426, and that sigma 3 is equal to minus 32,426 psi. Okay, so that's how we use Mohr's circle to calculate our principal stresses, and then we have to use our principal stresses to find and we'll use those in our failure theories. All right, now let's take a look at example 4-2, and this is where you can get into trouble if you calculate the wrong end plane shear stresses. Okay, so in this case we're told we have a biaxial state of stress. Sigma x is positive, and again it's 40,000 psi, and we're told sigma y is also positive, so this element is in tension in both directions, and it is 20,000 psi. So automatically, when I see this, I mean, I know that, you know, if I draw Mohr's circle, right, I have 2 points here that are my states of stress. So my third point is here. So if you're not careful, and we'll go through this, but you can calculate the wrong in-plane shear, okay? So in this case, we're also told that tau xy is positive. Okay, tau xy is equal to 10,000 psi. And the convention is that if it's a positive shear, then it wants to do cause your circle to rotate in the clockwise direction. So positive is clockwise. So I'm going to draw my tau xy's like this for my two points, you know, A and B on my faces. This is my A face and my B face. So then I can draw my circle, okay? But in the three-dimensional state of stress, I also have this circle here, because I have, this is now going to be sigma 1, this is going to be sigma 2, and my sigma 3 principal stress is 0. Okay, so what that means is I actually have a third circle here that is the envelope of that state of stress, and it has this radius here that is the max in plane stress. So I can find my principal stresses here, sigma 1 and sigma 2, using this Mohr's circle. Okay, so I'll find my center of this circle. Sigma c is sigma x plus sigma y over 2, and I can find the radius of that circle, and the radius of that circle is this radius here, okay, and that's the square root of sigma x minus sigma y over 2, that's x, sorry about that, squared, plus tau xy squared. And so sigma 1 is going to be my center plus the radius there, okay, and then sigma 2 is going to be the center minus the radius, okay, so that's sigma 2, sigma 1, and then I have sigma 3. And this is where you can get into trouble. If you calculate your max in-plane shear, you'd be getting this radius and not this outer radius from this purple circle. I know I've repeated myself now 3 times or so, but that is what you have to be careful for. Okay, so our tau max in this case is going to be the maximum of, okay, tau 1, 3, tau 2, 3, and tau 3, 2, or 1, 3. Okay, and that maximum is going to be sigma 1 minus sigma 3 absolute value over 2, which in this case is just equal to sigma 1 minus sigma 3, sigma 1 over 2, and that gives us the radius here, because this is this line here from the origin all the way to sigma 1, okay, that gives us the outer circle, and that gives us the max in-plane shear. Okay, so this is the max, that's the max shear, okay, versus the max shear that we get from the radius of this circle. So this is very, very, very important. So when you draw these Mohr circles, you'll get the right answer if you have compression and tension, as we saw in the other example, in the previous example, okay? Because it works out that sigma 1 and sigma 2 gives us this radius for the outer circle. In this case down here, example 4-2, when they're both in compression, I mean they're both in tension, okay, we have to consider this stress at 0. And in that case, our tau max is going to be the max of these principal stresses, and we have to take the max value here all the way to sigma 1/2 to get this radius here for your max shear that the element will experience. And that's what you have to use for your principal shear for your failure criteria. Okay, so that's just a quick discussion of those two examples. There's more discussion in the book. If this is new to you, or you've forgotten it, or you're still confused, then you need to spend some time with this, because if you can't calculate your principal stresses correctly, you can't do your failure criteria correctly, and you could underestimate the safety of your design.